Hello, I'm Justin Carbonera, and my presentation topic is the RSA problem leads to a trapdoor one-way function. An outline of tonight's presentation. First, we'll go over some background information that we need for the proof. Then we'll go over the RSA problem description. Then we'll go over the description of a trapdoor one-way function. And finally, we'll go over the RSA problem leading to the trapdoor one-way function proof. Some background information. P and Q are large random prime numbers of roughly the same size. N equals P times Q is called the RSA modulus. Recall that phi of n equals P minus 1 times Q minus 1 equals the size of Zn star, since Euler's totient function counts the positive integers less than or equal to n that are relatively prime to n, and P and Q are both prime. Let E be an odd number between 1 and phi of n such that the greatest common denominator of E and phi of n equals 1. Therefore, E is an element of Z phi of n star. Let D be such that E times D equals 1 mod phi of n. Notice that if phi of n is known, it's easy to compute D, but if phi of n is not known, then D is hard to compute. This means phi of n must be kept secret. This is because D can be used to compute the eth roots of a number modulo n. For example, suppose y equals x to the power e mod n, then y to the power d mod n equals x to the ed mod n equals x to the ed mod phi of n mod n equals x to the mod n. So without d, it's hard to compute the eth roots mod n. This is the RSA assumption. Note that the double NE can be made public, and computing the eth roots is still hard. This is because D is used as a trapdoor to easily compute the eth roots. This is the formal description of what we just went over in the last slides, the RSA assumption. The RSA function, you're given the RSA assumption, and the RSA function is defined as f of NE of x equals x to the power e mod n. So our function equals x to the power e mod n. We want to show that this RSA function, given the RSA assumption, gives us a trapdoor one-way function. Intuitively, a trapdoor one-way function acts like a one-way function, but it can be easily inverted if you have the special trapdoor value. Formally, a collection of trapdoor one-way functions is a family of functions that satisfy the following properties. It's easy to sample a function. It's easy to sample from the function's domain. The function itself is easy to evaluate. And the two more interesting properties, a trapdoor one-way function is hard to invert. This means that for all non-uniform PPT adversaries A, there's a negligible function mu such that for all n, the probability that the adversary can invert the function is less than mu of n. The fifth property is that our trapdoor function is easy to invert given the trapdoor. There exists an efficient algorithm that given I and the trapdoor t from gen and the output y can output the inverse of the function. We're now ready to begin the proof that the RSA problem leads to a trapdoor one-way function. We will do so by proving that each of the 5 previously mentioned properties that define a trapdoor one-way function hold for the RSA function, again assuming the RSA assumption. Properties 1, 2, and 3. Property 1, it's easy to sample a function. Generate 2 large primes, p and q. Compute the RSA modulus n equals p times q. Then use phi of n equals p minus 1 times q minus 1 to sample a random element from Z phi of n star. Property 2, it's easy to sample from domain. The domain is x such that x is an element of Zn star. Property 3, the RSA function fi equals x to the e mod n is easy to evaluate. This is true because this evaluation requires only one modular exponentiation. The fourth property, the RSA function fi equals x to the e mod n is hard to invert. This will be the bulk of the proof. Note that the RSA assumption states that it's difficult to compute the eth root of a random element y is in Zn star. In our case, we first pick the root, then compute y equals x to the e mod n. To show these two statements are equivalent, and therefore that fi equals fne of x is hard to invert, we need to show that the RSA function is a permutation of the elements of Zn star, which is to say a one-to-one mapping between x to the e mod n and Zn star, or it's bijective. If we show that the RSA function is a permutation of the elements of Zn star, we're also showing that the distributions xe from Zn star from the RSA function collection and ye from Zn star from the RSA assumption are identical, which would mean an adversary that could invert our RSA function could also break the RSA assumption. This is the contradiction that we're looking for in this proof. Again, remember, we began the proof by assuming that the RSA assumption holds. So, we've reduced our proof that the RSA function is hard to invert to a proof that the RSA function is a permutation of Zn star. E is an element of Z phi of n star from the RSA assumption. Since E is an element of this group, it must have an inverse. We'll denote this inverse D. E times D equals 1 mod phi of n. Consider the mapping of the inverse. Gne of x equals x to the d mod n. For all x in Zn star, Gne of Fne of x equals Gne of x to the e mod n, which equals x to the e mod n to the power d mod n, equals x to the power ed mod n, which equals x to the 1 mod phi of n mod n, since e times d equals 1 mod phi of n, which equals x mod n. Since the inverse Gne of x equals x to the d mod n maps directly to one element of Zn star, we have shown that the RSA function equals x to the e mod n is a permutation of Zn star. This means we've reached the contradiction that we desired, and therefore it's been shown that the RSA function is hard to invert. The fifth property, fi equals fne of x, the RSA function, is easy to invert with Trapdoor. We need to show there's an efficient algorithm that, given I in the trapdoor from gen and y, can output the inverse of the function. We'll let the trapdoor t equal d. The inverse of y equals y to the d mod n. Note that y equals x to the e mod n. So therefore, y to the d mod n equals x to the e mod n all to the power d mod n, which equals x to the power ed mod n. Recall that e times d equals 1 mod phi of n. Therefore, this all equals x to the power 1 mod phi of n mod n, which equals x to the mod n, which maps to x. Therefore, it's been shown that the RSA function fi equals fne of x is easy to invert with Trapdoor. So we've now proved all 5 properties. So in conclusion, since we've shown that the RSA problem gives a function that holds on all 5 properties of a Trapdoor one-way function, we have successfully shown that the RSA problem leads to a Trapdoor one-way function. Thank you.